Program contexts. Isolated machines. Originally, program contexts were small. Programs were written for standalone computers, and operators served programs. From the 1940s through the 60s, programs, such as operating systems and embedded systems, ran close to machines and extended the capabilities of machines. Programs were often thought of as shells, layers, or virtual machines, like in the THE operating system. Standalone computers. From the dawn of computing into the 1970s, computers largely stood alone. Human operators moved programs and data between computers using sneakernet and physical media like punch cards, magnetic tapes, and floppy disks. On behalf of machines. Originally, all programs were of the computer, by the computer, and for the computer. Into the 1970s, mainframe computers resided in cold rooms and were cared for by operators who manually adjusted programs for the computers and manually adjusted data for the programs. Programs did not interact with users, only with trained operators who acted as intermediaries. Into the 1970s, input and output required physical devices like line printers, punch cards, and magnetic tapes, which limited user interaction. In other words, computers resided in temples and were worshipped by acolytes. Programs ignored users because of circumstance and awareness rather than malintent. Stable contexts entail enduring programs. Hardware tends to remain stable because it doesn't spontaneously grow new abilities or expectations. When contexts, like technologies and markets, are stable, products can endure and companies can take their time to create great products. Both Bell telephone phone lines and General Electric light bulbs endured for a century nearly unchanged. With upwardly compatible computers, for example x86 based, hardware-oriented programs can potentially endure unchanged for many decades. With upwardly compatible virtual platforms, for example hardware emulators, Java, and .NET, programs can potentially endure forever. Networks and users. More recently, program contexts have grown enormously. Programs communicate directly with each other across networks and with users through graphical user interfaces. Matty Tedder wrote that computers and programs are not isolated. Quote, "They are part of a complex socio-technical system." Network computers. Since the 1970s, networks, and especially the Internet, have enabled programs to interact directly with each other and to access data in shared databases on remote machines. Increasingly, programs communicate directly with remote devices, such as pedometers and thermostats, in the Internet of Things, and with remote servers in the cloud. Networked programs must implement communication protocols, understand representations of remote data, and tolerate asynchrony, so networks increase program size and complexity. On behalf of people. Today, most programs are of the people, by the people, and for the people. Since the arrival of the Mac and Windows 3.0, many programs have emphasized user interactions. Computers come with keyboards, mice, graphical displays, game consoles, touchscreens, microphones, and speakers to promote user interaction. Programs run at a high level and extend the capabilities of people. Different users have different skills and training and need different functionality and information. Programs serve those users in diverse ways, spoon-feeding novices and presenting deep and subtle analysis to experts, so user interactions increase program size and complexity. Ephemeral contexts entail ephemeral programs. Hardware and software engineers continue to build new computers that have new capabilities and use new protocols. Users have insatiable cravings for novelty, and they continue to want more features and quality. When contexts, pure computers and user expectations, evolve continually, programs are ephemeral. They must continually be upgraded or replaced, and they can only provide short-term solutions. Today, fewer and fewer consumer products remain relevant for long. The fashion retailer Zara avoids planning and predicting altogether, striving to respond continually to the fashion on the street. Phone and tablet apps compete in fad-driven markets where being on top for a month or even a week can be major success. Both. In general, programs relate to both machines and users. Toward machines. Some programs emphasize machines and ignore users, especially operating system kernels, embedded systems, physics and chemistry simulations, tools for training neural networks, and satisfiability solvers. Yet many user-oriented programs also need to use computer hardware efficiently, for example when rendering 3D graphics for games and movies, and when querying databases. And programmers only write one line of code at a time, so as Niklaus Wirth noted, programming is extending a given system. toward users. Some programs emphasize users and ignore machines, especially web pages and mobile apps. Yet embedded programs can also be huge, containing all of the complexities and speculations of user programs. And most embedded programs must eventually get some information out to humans, for example, status, so that when things go wrong, the device can get fixed. Programs in autonomous cars must address both machines and people. Controlling the motions of a car is machine-oriented, while interacting with the environment includes dealing with other human drivers and pedestrians. Program descriptions, specifications, and algorithms. Algorithms are possibly the highest achievements of computer science, and so people naturally want to think of their programs as either algorithms or representations of algorithms. For example, Peter Denning and Craig Martell recently wrote, quote, "A program is an expression of an algorithm encoded for execution on a machine." Specifications describe common, stable problems. Problems that occur over and over in many different contexts merit taking the time and effort to solve well. Both sort and discrete Fourier transform describe problems that are widely encountered and have endured unchanged for centuries. Specifications are simple and precise. Ideally, specifications are simple, precise, and even minimal. The postcondition for sort could be, for all I, 0 less than I less than n, y sub I minus 1 is less than or equal to y sub I. The elements are ordered. And, for all e, the number of e's in y equals the number of e's in x. The elements are otherwise unchanged. The postcondition for discrete Fourier transform could be, for all j, 0 less than or equal to j less than n, y sub j equals the sum of k, 0 less than or equal to k less than n, x sub k e to the minus I 2 pi j k divided by n. These postconditions are trivial, even though very few people understand them. Specifications generally have pseudocode solutions. Most algorithm solutions are described by pseudocodes that spell out all of the important and sometimes tricky details. For example, Quicksort, Cooley-Tukey, and Secure Hash Algorithm 1 all describe specific solutions using pseudocodes. However, some algorithm solutions are more vague. Donald Knuth uses prose descriptions, so transliterating his algorithms into source code tends to be harder, though it remains straightforward. Recent algorithms for MaxFlow by James Orlin and for matrix multiplication by Virginia Williams provide only the sketchiest of pseudocodes, so transliterating them into source code can be truly difficult. Specifications often have many different solutions. Sort has quick, merge, insertion, shell, and thousands of other variations. Donald Knuth published a tome on the subject in 1972, and much has been learned since then. Discrete Fourier transform has literal, matrix multiply, Cooley-Tukey, Brun, and many other variations. Pseudocode solutions can take a long time. It took the brightest minds in computer science 59 years to go from Ted Harris and Frank Ross's 1954 specification of MaxFlow to James Orlin's 2013 OVE solution. Rudrata solved the Knight's Tour problem in the 800s, Leonard Euler solved the Königsberg Bridge problem in 1736, and Stephen Cook and Leonard Levin laid the foundations for NP completeness around 1971. Yet after more than a millennium, Hamiltonian cycle remains effectively unsolved. Pseudocode solutions are eternal. Because specifications remain valid forever, pseudocode solutions also remain valid forever. Anyone who wants their programs to endure eternally will naturally want them to be thought of as algorithms or representations of algorithms. Pseudocode validation is objective and deductive. Pseudocodes are objectively and deductively correct when algorithmists use mathematics to show that a pseudocode implements a specification. Even so, validation can be tricky. Algorithms often embody a lot of opaque mathematical or contextual knowledge. For example, fast Fourier transform, such as Cooley-Tukey and Brun, presume knowledge of advanced, if 250-year-old mathematics that very few programmers know and is not even mentioned in Sweebach. Few programmers understand matrix multiplication using FFTs. Algorithms hide complexity. Algorithms tend to combine simple, short, abstract specifications with tricky, long, detailed pseudocodes. In every algorithm that we know of, the specification is far shorter and far more abstract than the pseudocode. History. Until 1977, the best minds in computer science and software engineering equated algorithms with programs. In the late 1940s and early 50s, programs computed logarithm, trigonometry, and ballistic tables and were almost pure algorithm. Donald Knuth published the first volume of The Art of Computer Programming in 1968, proclaiming in the title that the finest programs are algorithms. Edsger Dijkstra published Structured Programming in 1972 and A Discipline of Programming in 1976, which used the term program and algorithm interchangeably. All of his examples were actually small algorithms, the most complex being 8 queens and convex home. In 1975, Fred Brooks published The Mythical Man Month, in which his example of good code transliterated a published sorting algorithm into PL1. And in 1976, Niklaus Wirth published a book titled Algorithms plus Data Structures equals Programs. These luminaries naturally thought of programs as algorithms because they all started their careers when tiny programs ran on tiny computers. In the academic world, small problems were discussed in one lecture and examined in one test. Though much less often today, luminaries continue to argue that programs are either algorithms or expressions of algorithms. Denning and Martel recently wrote that the design process transfers the idea of each algorithm from our heads into code patterns, or quote, the design of the machine. Requirements and scripts. Requirements are written in natural languages or technical shorthands and describe the goals of software projects. Requirements describe unique ephemeral problems. Requirements describe what should change during this project from the status quo toward the as yet unknown future. Analysts usually develop requirements uniquely for each project, and in general, requirements differ for every project. Nobody ever practices rewriting the requirements for the same project over and over. Rather, they move on to the next project. Requirements are arbitrary. What users want is arbitrary and often murky. Users could want to improve existing features or to create whole new features, or any combination thereof. No guarantees exist that users won't change their minds halfway through the project. No guarantees exist that different users won't want totally different requirements. Requirements usually have script solutions. Whether written in C, Java, Python, or Ada, most source codes are actually ad hoc scripts that glue together and invoke known algorithms. For example, the requirement, "the button shall use the text in the input box as the key to fetch the remote data," describes the glue that will eventually invoke a series of algorithms to compress, transmit, error correct, parse, and display data. Requirements usually have one solution. In general, only one project, script, or body of code will ever get built for any set of requirements. An analyst might occasionally copy some requirements from one project to another, but he or she runs the risk of making the usual copy and paste errors. Nobody ever spends decades re-implementing the same requirements over and over looking for better solutions. Rather, all problems in the results of one project become new requirements for upgrade projects. Script solutions must be timely. Requirements express priorities by describing the features that should be worked on now in this project as opposed to later or never. Rarely will anyone wait years for a program to get written. No requirement should ever presume a solution to an unsolved problem, such as satisfiability, which remains open-ended research. Script solutions are ephemeral. A script only endures as long as users need the requirements that define the script. When users change platforms, for example, when users upgrade from MS-DOS to Windows or Android, older programs, scripts, become irrelevant and eventually die. So quality for script solutions emphasizes short-term utility rather than eternal correctness. Requirement validation is inductive and subjective. In practice, requirements are often quite horrible, having many erroneous, missing, and ambiguous details. Validation of a set of requirements shows that they describe a future program that will satisfy the future needs of users. Analysts can survey users about whether a specific set of requirements expresses their needs, but such surveys produce inductive truth. Nobody can ever prove that requirements describe what users will actually need because inductive truth can never become deductive truth. Such surveys are fraught because humans have many systemic biases, such as the availability and self-serving biases, and humans all too often make mistakes, even if unintentionally. Requirements are subjectively correct at best. Putting a validation check on one button and not on another has everything to do with what users say they want via the requirements, and nothing to do with any objective concept like hardware, operating systems, libraries, pseudocodes, or mathematics. Programs expose complexity. Analysts should express every important visible detail of the project clearly in the requirements and should avoid compression and implication. Otherwise, programmers might overlook or forget the hidden and implied details. This makes requirements large. Requirements often unintentionally leave many details unstated, such as the interconnections between requirements, but such omissions all too often cause problems later. Similarly, source codes must express every important and visible detail needed to make the program work properly. History. Since 1977, people have argued that programs or scripts differ from algorithms in fundamental ways. In 1977, Richard DeMello, Richard Lipton, and Alan Perlis published Social Processes and Proofs of Theorems in Programs about the differences between mathematics and programming. In 1988, James Fetzer published Program Verification, the Very Idea, about the differences between logical structure of an algorithm and the physical control of a program. In 1996, Brian Smith published On the Origin of Objects about the differences between models and things. Matty Tedder elaborates on this history. Today, almost everyone, outside of formal specification and model-driven communities, accepts that programs differ from algorithms. But researchers will forever attempt to shift the boundary between programs and algorithms because that is part of their jobs. Both. Programs have always combined algorithms with scripts, and they always will. All projects need specifications and algorithms. Small embedded programs for signal processing and secure communication are often nearly pure algorithm. Large programs usually invoke many algorithms. For example, sort is used all over the place in most large programs. Libraries of string and matrix functions contain many algorithms. Even programs that do pure arbitrary interaction, such as Hello World, use algorithms for input and output. Users and programmers are often unaware of the algorithms that get invoked, for example, when they use secure communication. All projects need requirements and scripts. Someone needs to define the goals of each project, even when the result is essentially pure algorithm. For example, when users want to compute Fourier transforms, someone needs to state clearly that the program should compute Fourier transforms rather than, say, cosine or wavelet transforms. Requirements describe how scripts should glue algorithms together, how to move data from one algorithm to the next, under what conditions to invoke each algorithm, and so on. Most algorithms are already shared in libraries, so software engineers rarely implement algorithms anymore. As time goes on, less of programming relates to algorithms and more relates to scripts. Tools. Tools. Tools are powerful and consistent. Tools have lots of power under the hood and can consistently apply sophisticated algorithms, optimizations, and searches, managing enormous quantities of detail and complexity that human brains simply cannot keep up with. Compilers and optimizers are imperfect, yet they consistently outperform humans at generating correct and fast assembly code. IDEs can search through and refactor enormous code bases flawlessly. Repositories can store and retrieve the history of large code bases more swiftly and accurately than developers could ever remember or imagine. Tools counter human flaws. Many software tools counter the flaws in developers. For example, high-level languages and IDEs enable developers to do more work, improving productivity. Type checkers and linters catch many routine mistakes, improving quality. And metrics encourage developers to work steadily and overtly, improving accountability. The SE profession is defined by tools. Tools have always driven progress in computing, and everyone more or less defines software engineering in terms of tools. For example, Denning and Martel argue that people define computing by the core technologies of algorithms, programming languages, databases, graphics, and so on. SE jobs are defined by tools. Today, HR departments mainly define developer jobs by tools. Job descriptions usually list the languages and tools that new hires will need to use. For example, quote, candidates should know Rust, Rails, containers, blockchain, and Eclipse. HR personnel emphasize tools because they can trivially compare keywords on resumes, but cannot otherwise evaluate the skills of unknown candidates. Limits of tools. Tools only do repetitive, well-defined work. Increasingly, software engineers realize that tools automate the common, easy, well-defined, repetitive, algorithmic, deterministic tasks like compiling, type checking, building, storing, and searching. Tasks that get done only once or cannot be defined precisely, such as solve the user's problem, don't get built into tools. Tools don't understand intention. Tools cannot create value on their own because they do not understand human intentions and cannot guess the purposes behind the changes to code. Requirements and estimation tools do not know which details are missing, wrong, ambiguous, or destined to change because they do not know what users actually want. IDEs cannot do the typing for programmers because they have never been able to guess user or programmer intentions. Predictive typing on smartphones is still only 10% accurate. Compilers cannot generate the assembly code that users actually want because they cannot deduce what programmers meant to write. Repository tools cannot reliably merge changes on their own because they do not know the intentions behind the changes to source codes. Testing tools for GUIs and web pages help, but do not actually know whether a program does what users want. Tools are overwhelming. Software engineers don't understand most of their tools. Few practitioners truly understand branching and merging in repositories. They often use repository tools in ad hoc ways and often do lots of unnecessary work. Updating Eclipse packages too often becomes a nightmare of bizarre dependencies. Microsoft Word can do anything, but it is so huge that many simple tasks remain beyond understanding, such as page headers and footers for books. General purpose languages are overwhelming. C++ is now infinitely large, and nobody understands it all anymore. Java is getting that way. Skills. Programmers understand the needs of users. Only software engineers can interpret or figure out the needs of users and write the appropriate code. Software engineers create value by spanning the gap from intention to code and by applying tools on behalf of users. Programmers do bespoke, problem-specific work. Humans have always picked up where tools leave off, filling in for the limitations of tools. Tasks that are hard, such as solving NP, or poorly defined, such as figuring out what users actually need and then writing the random code to implement it, won't get automated by tools because that remains impossible. The SE profession should be defined by human skill. Today, the most important resource in software development is the mind, its knowledge, experience, attention span, and so on, all of which are limited. SE jobs should be defined by human skills. Before the 1980s, before software tools became so specialized and elaborate, job requirements for programmers were primarily experienced, driven, willing to learn. These attributes will always remain essential, even though nobody knows how to evaluate them effectively. Both. In general, software engineers need both tools and skills. Tools. Tools are vital and have always supported developers. In general, developers write more and higher quality code using Java and Eclipse than using assembler and card punches. Type checkers and linters can quickly and reliably verify type safety, which is an important first step toward making useful programs. Practitioners should know the concepts behind core tools like languages and IDEs very well, and the concepts behind many other tools like repositories at least tolerably. Skills. Tools are not enough on their own. They must also be applied effectively, even artistically. Developers must use their experience and drive to pick up where tools leave off, to write the useful code that solves actual user problems. Software engineers should also use at least some tools, like IDEs and languages, with ease to avoid digging out the manual for every task. And they should type proficiently. Practices. Rules. In a deterministic world, rules keep developers on the straight and narrow to improve productivity and quality. Rules document fixed units of human activity as processes and fixed units of knowledge as scripts. Organizations benefit both from documenting common problem solution pairs and from responding to similar problems consistently. Repetitive processes. Bertrand Meyer argued that the term practice refers to, quote, repeated activities. Most processes focus on what analysts, developers, and testers routinely do. Task-level loops, for example, Beck's extreme programming, include get next task, implement it using test-driven development, inspect it, check it in, and do the paperwork. Iteration-level loops, for example, Sutherland and Schwaber's Scrum, include plan the iteration, do the work, retrospect the iteration, and improve the process. Quarterly release loops, for example, Bame's spiral model, include plan the release, do risk analysis, do the work, test the results, retrospect the release, and improve the process. Ad hoc processes. Many development tasks occur infrequently, such as quarterly versioning of DLLs, or even just once, such as individual process improvements and one-off customizations. Documenting tasks that occur infrequently helps to ensure that solutions don't get forgotten, but everyone should remain skeptical that such tasks ever get documented accurately or carried out with ease. History. Processes. In the early days of computing, say before 1968, practices came from personal experience and individuals applied them inconsistently. The NATO conferences on software engineering inspired immediate progress on processes. Winston Royce wrote about improving waterfalls in 1970. The CAP Gemini SDM from Pandata from 1970 might be the first true software development process. Structured analysis and design method was initially developed in the late 1960s and was published around 1980, and the capability maturity model was published in 1989. Processes are software. Leon Osterweil published a classic paper in 1987 arguing that processes are software too. His metaphor has a bright side. Documented processes reveal the current state of practice, and they can be incrementally improved like programs. But his metaphor also has a dark side. It implies that programmers are robots who merely do what they are told, and that their work can be defined deterministically. He reinforced the rational behaviorism view of people. Patterns. Kent Beck and Ward Cunningham started the software patterns movement when they presented using pattern languages for object-oriented programs in 1987. The Design Patterns book from 1994 documented the common substructures that occur inside of large objects or classes, especially ones that occur in GUIs. The patterns movement reinforced the scripts movement. Scripts. Scripts can describe anything worth remembering and often contain flowcharts or programs that treat people like programmable computers. Boehm and Turner give example scripts for a quality process manager role and an inspection process. Barry Boehm and Richard Turner argued that bright and well-intentioned but inexperienced people can merely follow scripts and write great software. Many organizations strive to document all of their institutional knowledge, building enormous databases of scripts. IBM was renowned for its comprehensive documentation in the 1950s, which led the U.S. military to select them to build Sage. Script databases have become more and more common since the Internet made them widely shareable. Scripts remain widely used in sales and support organizations. Limits of rules. Increasingly, everyone realizes that processes and scripts have severe limits. Process and script databases fail for essentially the same reasons that encyclopedias fail. Gaps. Many rules are missing or contain gaps. In real projects, in rapidly changing and complex fields, new situations and special cases arise all the time. More prosaically, the situation anyone is experiencing right now has all too often never occurred to him or her before, and surprisingly often has never occurred to anyone he or she knows. Historically, IBMers joked about the, quote, great oral tradition, all of the corporate knowledge that remained undocumented. Errors. Scripts all too often contain contradictory, out-of-date, wrong, or vague details. Maintaining large sets of scripts takes a lot of work, which rarely occurs. Overwhelming. Rules easily become overwhelming. Ideally, everyone would consider all of the rules in the corporate knowledge base, IEEE standards, and their personal experience before making each decision or typing each line of code. But they cannot. When these knowledge sources have thousands or tens of thousands of rules, nobody can know them all, let alone take time to consider them all. Daniel Kahneman argued that people should only ever consider 5 to 7 rules at a time, because that is the limit of human working memory. When too many processes and scripts get documented, they just add noise and sow confusion. Demotivating. Psychologists have shown that nobody has ever been motivated to excellence by a 3-ring binder or a database full of rules. The processes inspired by CMM, ISO 9001, and TQM were often just put on shelves and forgotten. On the other hand, people are inspired by things like cultures and goals. Hard. Documenting processes and knowledge well is really hard because good documentation takes more time and effort than almost anyone has patience for. While most software engineers can type, in our experience, very few take the time and energy to write well. Judgments. Since rules cannot document all of the problem-solution pairs for coping with the actual situations and surprises that will occur in the next project, everyone also needs judgment. Judgments both fill in the gaps between rules and work around the errors within rules. Technical examples. Bertrand Meyer wrote, quote, "Sometimes it is better to fix each problem, and sometimes it is better to move on. But choosing which is best in each specific situation requires judgment." To fix bug ABC, one could type line of code X here or line of code Y there, but deciding which is best requires judgment. Social examples. Susan Nyman writes, quote, "Deciding how to treat someone is enormously complicated. As programs become more user-oriented, social interactions with end users matter more, and developers need better social judgment. But developers often do social work much more poorly than technical work. For example, in CRM projects, talking with users in the sales and support departments differs greatly from talking with colleagues in the IT department. The conversation skills that put users at ease and evoke meaningful information won't ever come from scripts." Think for yourself. Susan Nyman writes, quote, "How do you use good judgment? Think for yourself. Quote, without judgment, you don't know how to apply the principles you know. Good judgment is common sense, and stupidity is lack of judgment. When decisions matter, everyone should use their judgments and best guesses. They should also be aware and honest that they do so, and perhaps also get colleagues to collaborate on or review their work." History. Throughout history, many people have argued that judgment matters more than rules. In Phaedrus, Plato said, quote, "If men learn writing, it will implant forgetfulness in their souls. What you have discovered is a recipe not for memory, but for reminder, and it is no true wisdom that you offer your disciples, but only its semblance. For the most part, they know nothing." In the 1700s, Immanuel Kant wrote that judgment is what links general principles with specific situations, i.e., theory with practice. Charles McCabe wrote, quote, "Any clod can have the facts. Having opinions is an art." The pattern and script movements have created tsunamis of rules, and practitioners increasingly feel overwhelmed and recognize the need for judgment. Both. In general, software engineers need both rules and judgments. Rules. Rules remain essential for sharing knowledge and training. A searchable database of scripts can provide hints for coping with new situations when someone else has encountered similar problems from the past. Nyman argued that examples are crucial for developing judgment, and script databases document many such examples. Daniel Kahneman and Amos Tversky noted that human judgment is fraught with systemic bias, and so everyone should use rules whenever they can. Judgments. Judgments must always override rules and scripts. Software engineers must always decide whether and when to apply each rule, which requires judgment. Many situations encountered in typical projects lie beyond the documented rules, and judgment enables analysts, programmers, and testers to cope. Organizations. Factories. Structure. Factory processes, like clean room and rational unified process, attempt to improve productivity, quality, and control within projects by imposing structure on both the workers and the work. Offices. Factories embed workers in large office-based organizations. Before the internet, offices were essential for making software because people went to offices to access shared computers and to communicate with colleagues. Offices also enabled people to separate work and home life. Capital. From the dawn of computing through the 1990s, computers and software tools, and especially case tools, were expensive. Factories provided these expensive tools to workers, which was capitalism at its finest. Even today, Google and Microsoft build their own supercomputers for analyzing web data and training neural networks. Workers are cogs. Bertrand Meyer noted that cross-functional teams can be difficult for managers who would rather have the flexibility to assign workers wherever they want. Managers and HR personnel hate the purple squirrel problem of having to find a different worker for each distinct, unique position. Defining ideal workers as interchangeable cogs simplifies the work for managers and HR personnel. Certifications reinforce the status quo. Bayman Turner noted that training, certifications, and professionalism concern developing and proving proficiency at common skills that everyone should know, which enables managers to assign workers to tasks freely. Certifications and professionalism reinforce the presumption that workers are interchangeable cogs. Metrics reveal reality. In meritocracies, people want to distinguish between those who do good work and those who are merely pals with the boss. Metrics, like Scampi, attempt to reveal the truth of productivity and quality objectively. Rigid class distinctions. Distinguishing between those who control a factory and those who work in a factory exaggerates class distinctions between managers and developers, and so managers naturally prefer factories to enhance their statuses. Leaders plan. In a deterministic world, the future is predictable, so plans and estimates can be and should be accurate. Leaders at upper levels of projects and organizations use plans and architectures to predict and control the future. Workers follow. In a deterministic world, workers resemble actors following scripts by William Shakespeare, musicians following scores by Ludwig van Beethoven, or construction workers following blueprints by Philip Johnson. Ideal workers strive to follow the lead of managers and architects and to meet expectations and standards. Workshops. Flexibility. Workshops provide flexible spaces for artisans to collaborate and to respond to whatever challenges arise. Denning and Martel recently wrote, "Good programming is an artisan skill developed with good training and years of practice." Gigs. As inexpensive high-speed internet access and software tools have become widely available, programmers can work independently of factories. They can work remotely from almost anywhere in the world, increasingly from coffee shops or home offices. In the gig economy, practitioners increasingly work project to project. Everyone takes their phones and computers home, so separating work and home life becomes more difficult. No capital. Today, everyone uses tools and practices for nearly free. As the prices of computers and software tools have plummeted, more and more practitioners can afford to acquire their own toolkits. In the late 1970s, $2,000 bought a personal computer, much less today. Free and inexpensive software tools such as the GNU toolchain, Java, Eclipse, and GitHub are available to everyone, and they facilitate open source projects. Documentation about contemporary practices is widely available online. In many projects today, developers use their own resources, often called Bring Your Own Device, BYOD. However, artisans remain unable to do capital-intensive projects on their own. Workers are snowflakes. Every worker has unique strengths that should be exploited by cross-functional teams. As each practitioner gains experience in his or her own situation-specific ways, those skills slowly become more specialized and idiosyncratic. Ideal workers differ for each project. Skills at the current project, which matters most, cannot be measured by metrics or proven by credentials. Experience and enthusiasm. Humans are limited by their abilities to learn what they need to learn, to adapt and overcome new situations that they do not yet understand. Both experience and enthusiasm contribute to effective solutions. Unfortunately, resumes and certifications cannot reveal whether anyone has the experience and drive necessary to contribute effectively to any given project. Metrics distort reality. No metric has ever inspired anyone to excellence, not even Scampi. All metrics must be gamed because anyone who doesn't play the game gives their rivals a leg up. Metrics distort reality because the artificial game becomes the new reality. One problem is that the same people tend to excel at playing each particular game, and so the same people always appear to perform best when judged by any given metric. Within each organization, performance awards tend to reinforce the status quo, which can seem unfair and demoralize everyone else. Tweaking metrics to give other people a chance increases the politics and tends to make everyone mad. Murky class distinction. In artisan workshops, the divisions of labor and class distinctions between managers and workers are murky and fluid, so programmers naturally prefer workshops to enhance their statuses. Everyone engages. In an emergent reality, everyone struggles to keep their feet as the ever-changing world tries to shake them loose. During projects, they strive to deal with the changes that get revealed as ongoing and seemingly random surprises. Project team members resemble actors in improv theaters, musicians in jazz bands, athletes on basketball courts, or rafters on rapids. Everyone tries to contribute to the group and to solo in turn. Even working on a single task resembles surfers riding waves or cowboys riding broncos. Constraints always exist, but individual choices matter and they add up fast. Ideal workers strive for appropriateness and timeliness. Both. Everyone wants practitioners to focus on the work, and so in general, software development organizations should function both as factories and as workshops. Factories. Everyone wants the large-scale division of labor of factories for project assignments and payroll. For example, in CRM projects, team members want to avoid the politics of defining projects and to avoid the sales and business aspects of acquiring resources. In addition, capital remains essential for paying salaries. Workshops. Within most projects, team members behave as workshop artisans to do the work. Artisans bring their experiences and enthusiasms to each project, filling in and helping each other to do whatever needs to be done. Management. Scientific. Scientific management works better for projects that are primarily opportunity bound and have ample resources. It emphasizes reductionistic and fully funded projects. Reproducing existing products. Scientific management seems most effective when reproducing existing products, such as when expanding from making one copy of a product to making many copies. The only way to accurately plan projects is to do them twice, so the second time around everyone can start out with reasonable expectations. For example, industrial engineers can have reasonable expectations when they expand from making one car to making many cars. Software administrators can have reasonable expectations when they expand from installing a program on one computer to installing it on many computers. Scientific management primarily sustains the status quo. Perfecting means doing everything. Scientific management judges quality relative to perfection. Ideally, projects would give all users everything that they want and make them totally happy. Omitting even one feature lowers satisfaction. Ideally, analysts, developers, and testers would do all possible activities, planning, designing, inspecting, tracing, testing, and so on, for every single detail, regardless of size or risk, tracking down and fixing every last possible flaw. Omitting even one step, like requirements tracing or regression testing, opens up opportunities for error. Top dog strategy. Top dogs strive to use their resources as entry barriers to block competitors from succeeding. They strive to convince competitors to play the same resource-driven game. The SEI persuaded Europe to fund the ESI for a while, but they were unable to hoodwink Japan. Only India's Tata had enough low-cost manpower and experience with bureaucracy to beat the SEI at their own game. Quality is free. Capers-Jones and Watts-Humphrey were both inspired by Philip Crosby's book Quality is Free. Jones argued that improving quality would lower cost, which works in deterministic contexts like factories. History. The concept of scientific management came mostly from the United States. After World War II, the U.S. had the only developed economy whose industry remained intact. For decades thereafter, it maintained a huge resource advantage compared to all other economies. Frederick Taylor was an American mechanical engineer and steel plant manager interested in industrial efficiency who advocated for scientific management in the late 1800s. Henry Ford applied the factory model to automobile production in the early 1900s, which succeeded because the reasons for putting the engine and seats into each car are mostly alike. Watts-Humphrey applied the factory model to software development in the late 1900s, which failed because the reasons for putting each line of code into a program are mostly different. Lean. Lean management works better for projects that are primarily resource-bound and yet have ample opportunities, for example, where many different solutions could work. When limited resources must satisfy vague aspirations or enormous expectations, projects are effectively resource-bound and they can only provide partial or short-term solutions. Creating new projects. Lean management seems most effective when creating innovative or new products, such as when expanding from 0 copies of a product to 1 copy. Resource limitations occur frequently in startup companies that struggle to create new products, so many entrepreneurs use variations on the lean startup methodology. Lean management primarily facilitates emergence. Satisficing means doing only the most important things. Lean management judges quality relative to failure and emphasizes the pragmatics of satisficing, or doing good enough work for now, for this specific situation. For example, satisficers may provide partial solutions. They may address the symptoms rather than the underlying problems, or they may provide cheaper short-term solutions rather than more expensive long-term solutions. When problems are resource-bound, managers and developers must continually make hard choices to solve the highest priority, most important issues now, and to defer or cancel everything else. Satisficing contradicts many of the ideals of perfection and correctness. Users always want as many features and as much quality as they can get, which means more than developers can possibly deliver. Users will grumble about all finished programs because no matter when development stops, someone will still want more. Dropping any feature reduces functionality. Dropping any step increases opportunity for error. For example, developers may only do tracing and regression testing on the most critical components, but resource-bound projects simply cannot afford to do everything, and so projects necessarily drop a lot of features and steps. Projects are abandoned when resources run out, rather like proverbial novels and movie scripts. Underdog strategies. Underdogs rarely have many resources and often have little more than determination. To succeed and upset the status quo, they must endure and strive to exploit the opportunities that arise. Toyota proves that lean can also work as a top dog strategy. Quality is expensive. Software quality corresponds to more features and fewer bugs. The ongoing maintenance that improves quality invariably costs a lot. Brian Randall noted that many software applications are only usable after the third release, such as Windows or Office or Salesforce, which shows just how hard and expensive quality really is. History. The concept of lean management mostly came from Japan when resources were scarce. Before World War II, the Japanese economy was still developing rapidly, and after World War II, it was devastated. Throughout the mid-20th century, Japanese companies needed to find their own ways to compete, and they learned to thrive by using pragmatic, flexible, opportunistic processes. Lean may have started as early as 1934 when Toyota produced its first car, though lean was most famously used in the decades after World War II. Lean started as a manufacturing practice more than half a century before it started as a software practice. In 1986, Hirotaka Takeuchi and Ikujiro Nanaka, two Japanese business professors working in the United States, shared their concept of Scrum processes in the Harvard Business Review. Scrum started as a business practice for product development nearly a decade before it started as a software practice. Both. In general, everyone wants quality, but depending on their specific situations, they want or can tolerate different combinations of perfection and good enough. In other words, most projects need both some scientific and some lean quality. Scientific. In our experience, all software projects have some core functionality that must get implemented exactly right in the scientific sense. Web API callouts usually must work exactly right to work at all, and developers should close all major security holes. Lean. In our experience, all software projects encounter hidden expectations, changes in goals, mistakes in planning, and so on. In effect, users and managers always want more features and quality than their initial budgets and schedules allow. In our experience, all software projects have at least some flexibility in the requirements that should be delivered. Everyone should satisfice appropriately and use their limited resources as well as they can to maximize the benefits to users. Design. Reductionism. In a deterministic and non-fractal world, reductionist approaches to design often work. In reductionistic systems, the whole equals the sum of the parts, and so project plans can fully describe a fixed series of known discrete tasks that encompass all of the work. Plans and estimates based on decomposition into parts should be accurate. Small, robust, and known. Reductionism requires that projects and systems be relatively small, i.e., that they have relatively few and relatively large parts. It requires that interfaces are stable and robust so that changes and errors can be localized. It requires that no unknown unknowns exist so that significant surprises cannot occur. These conditions occur most often in small systems with few top-level parts, like toys, or in enduring systems that have well-developed internal structures, like cars. Toy examples. Toys and activities for children are usually reductionistic. Paint-by-number sets, Lego blocks, and jigsaw puzzles all constrain the possibilities for success and for failure by restricting the top level to few and large parts. Automobile example. Automobile factories are reductionistic. Automobile factories are more than a century old, and cars have well-developed and stable internal structures. The steps of an assembly line that build whole cars include welding the frame, painting the sheet metal, and adding the engines, seats, and tires. Automobile factories have a couple hundred steps at most, Engines, tires, and seats are relatively large components that have stable and robust interfaces and that get built in other, simpler factories. Factories can now easily swap out paints, engines, and tires from one car to the next. Opportunities for error are limited on an assembly line, yet even so, automobile factories have stations to detect and fix problems. Software examples. Factory and waterfall processes embody reductionism by breaking projects into discrete stages or steps that fully encompass all work. Machine-oriented and embedded programs that do encryption, signal processing, and compiling have small and stable interfaces. Compilers have well-understood components like lexers, parsers, symbol tables, and code generators, as documented in the Dragon books. Stable contexts. Determinism and reductionism idealize shopping or selecting among existing parts. Component-based development idealizes assembling programs from a catalog of parts, like erector sets. Holism. In an emergent world, reductionistic approaches to design don't work. Kurt Kafka defined holistic systems with, quote, "The whole is different than, or more than, the sum of its parts." Taking a holistic system apart changes something important. When goals are vague or missing or cannot be reduced to a small number of discrete existing parts, then plans and estimates cannot be accurate. Large, sensitive unknown. Holism tends to occur for relatively large systems, i.e., systems that have relatively many or relatively small parts. It tends to occur when using new components that lack robust, stable interfaces, so changes and errors can easily ripple throughout the system. It tends to occur when many unknown unknowns exist. Until these unknown unknowns are revealed, developers cannot deliberately set out to solve them. These conditions occur most often for large systems that have many top-level parts or for new systems that have poorly defined internal structures. Tool example. Tools and activities for adults are often holistic. Artists confronted with a blank canvas and a palette of oils could paint almost anything. Writers confronted with a blank page and a word processor could type almost anything. Adult tools and activities expand the possibilities for success and failure as far as possible. Software example. Most programs have many, many lines of code, and each line of code must work exactly right. In 10K line programs, lines of code are relatively small compared to whole programs. There are many, many ways that source code can go wrong. In almost all software projects, requirements and architectures are sketches that have many unstated, ambiguous, or misstated details. In other words, many unknown unknowns. Large programs are actually large systems that have too many potential problems to guarantee avoiding or fixing them all. History. Herbert Simon noted that after World War I, Gestalt, holism, and creative evolution were developed. After World War II, feedback and general systems theory were developed. More recently, in the 1980s, chaos and adaptive systems were developed. Evolving contexts. Refinement and holism work best for programs that respond to evolving contexts, such as competitive markets and customizations. Customization means doing new work that does not already exist in the codebase. The new work is often used just once. Both. In general, software projects should have both reductionistic and holistic elements. Reductionism. Reductionism means that developers can effectively organize large source codes into semi-independent pieces. Without some reductionism, large software projects would be big balls of mud, too complicated and expensive to attempt. Holism. Holism means that programs are more than the sum of their parts, and that the synergy between different parts provides emergent benefits to users. If software were completely reductionistic, there would be few benefits to building large programs, and small Unix programs combined with pipes could solve all problems. Notes. The lamppost problem. The IEEE SWBOC and CSDP, or PSEM, like all standards and certifications in complex fields, suffer from the lamppost problem. One searches for one's lost car keys near a lamppost because everything near the lamppost is visible in the light and known, and everything else is invisible in the dark and unknown. Everything described in SWBOC and tested by CSDP is correct and important, and everything else does not exist, or in other words, is effectively wrong or unimportant. Emphasizing determinism. SWBOC links professionalism, accreditation, and licensing with determinism. All topics in a body of knowledge must have known and correct answers so that someone can document, teach, and test them, which is why Sweebach focuses on existing tools and rules. Sweebach states that everything important about software engineering is already known and enumerated in Sweebach and other IEEE standards. Ignoring emergence. Sweebach and CSDP effectively deny that emergent concepts such as skills and judgment matter. Since CSDP never expires, it effectively claims to test for all knowledge that will ever be needed by anyone in a project. But emergent concepts cannot be documented, taught, or certified because nobody knows what they are yet. The editors cannot acknowledge that emergent concepts matter because that would mean that Sweebach and CSDP do not reveal everything that professionals need to know. Developer questions. How should one cope with the vagaries of real projects? What will change during a project? What errors will occur during a project? What new technologies will arise? What should one do when users cannot articulate their needs? What should one do when users are unrealistically demanding? What should one do when project funding gets cut in half or overruns get revealed? Manager questions. How should one motivate team members? Do you challenge, demand, ignore, engage, bust chops, bribe, plead? What? What should one do if a team member has spring fever? What should one do if a team member is going through a divorce? What should one do if two or more developers want the same promotion, given that the losers often quit? The answers to all of these questions are, it depends on the specific situation and the specific people involved, and the solutions are simply impossible to document, teach, or certify. Skills, judgments, enlightened management, and dealing with unknowns are deemed unimportant in Sweebach and are untested in CSDP. They effectively deny that hard problems, unknown unknowns, and emergence exist. Sweebach and CSDP cannot predict the future. The future of individuals. Certifications presume that tests from the past do signify whether someone will contribute to the successful projects of the future. Quote, professional certification also can verify the holder's ability to meet professional standards and to apply professional judgment. Professional judgment is defined by an exam about the contents of Sweebach. The future of projects. In fact, certifications like CSDP do reveal that someone did a lot of work in the past, which can be an excellent heuristic that they will also do well in the future. But it doesn't actually reveal what will happen on any given project because nothing can do so. CSDP doesn't reveal whether anyone will have the necessary flexibility, imagination, enthusiasm, and grace under pressure. Sweebach actually claims that people can resolve all uncertainties by consulting textbooks, journals, colleagues, and stakeholders, or through some magical form of risk management. The future of the profession. The authors of Sweebach describe ideas that were true in the past, and they presume that those ideas will accurately describe software engineering until the next update, usually 10 years later. The authors of Sweebach should be proud of their efforts because it took a lot of work, and it usefully describes a large chunk of software engineering. But they should not be too proud, because Sweebach ignores the emergent half of the profession, and on average, half of what they do describe is wrong because it expires in half-life patterns. We find it interesting that ancient Chinese civil service exams had open-ended essay questions to evoke judgment, while CSDP and PSEM exams are multiple guess to minimize judgment. Perception is reality. Whether determinism and emergence are realities or concepts of reality is actually irrelevant to this chapter. In the first draft, we described determinism and emergence as realities. However, almost every reviewer gave us grief. So in this draft, we describe determinism and emergence as concepts of reality because that seems the easiest way to avoid those objections. However, we actually believe that determinism and emergence are realities rather than concepts of reality because we believe that perception is reality. According to psychologists, people perceive the world through their mental models, so beliefs are tools like telescopes and microscopes that enable people to perceive and to manipulate their environments. Beliefs influence what people expect is possible and what they believe should be done. One reviewer argued that, quote, factories and agile are ideas, and ideas are there to serve purposes. We would agree, except that those ideas influence perceptions and expectations, and so those ideas also define realities. Too many conflicting ideas about software engineering are floating around for anyone to coherently wrap their minds around all of them at once. The subset of possible ideas that anyone actually believes defines his or her reality. So every software engineer effectively lives in his or her own unique reality. The folks at the SEI value managers and architects and planning. We, the authors, value programming and coping. They value different things than we do, and so they live in different realities than we do. A common ground state that underlies both determinism and emergence may actually exist, like a computer that can underlie both an embedded system and a video game. However, we don't bother looking for it. Philosophers and scientists have been debating determinism and emergence for at least 2.5 millennia, and they haven't found such a ground state yet, so we wouldn't expect to find one either. People don't only believe one thing. We use quotes to show that at one point or another someone articulated each specific idea. We do not mean to imply that anyone held only that single point of view. All quotes are taken out of context and may not accurately express the intentions of the authors. Most believe in both. Most people seem to believe in both determinism and emergence. Confucius emphasized determinism in his rituals, yet he also supposedly said, quote, "Study the past if you would define the future," which some have interpreted as support for emergence, though we do not. Lao Tzu emphasized emergence, but his observations about accepting change also apply to accepting one's fate in a deterministic world. Aristotle believed in a deterministic universe driven by clockwork mechanics, and also in an emergent universe driven by chance events. Tony Hoare is mostly known for his work on algorithms and formal verification, which align with determinism, yet he also wrote, quote, "The most important property of a program is whether it accomplishes the intentions of its user, which aligns with emergence." Most change their minds. Most everyone changes their minds from time to time. For example, while writing the first draft of this chapter, we associated patterns with emergence because they were developed at around the same time and by the same people who also developed early agile processes. But after hearing a researcher at Microsoft comment on some of the problems with patterns, we came to associate patterns with determinism. In the first draft of this chapter, we argued that agile and emergence had vanquished waterfall and determinism, but Robert Schaefer and Will Trace pointed out the continuing value of waterfalls in determinism. After getting their feedback and reading the books The Path and Trying Not to Try, we changed our minds. In the second draft, we attempt to support both equally. We suspect that many others change their minds on occasion too. As determinism grows, emergence also grows. The basic level rises continually. The basic level is the relationship between analysts, developers, testers, and their algorithms, tools, and practices. Since the mid-1940s, the basic level for programming has risen steadily. Programmers changed from using cables and switches on the ENIAC to using machine code on the SSEM to Fortran on the IBM 704 to using Java on Android. Programmers developed algorithms, data structures, abstract data types, operating systems, libraries, patterns, IDEs, code repositories, processes, and reuse. The basic level will continue to rise as long as algorithms, tools, and practices continue to improve. Shallow technologies. As software technologies rise in level and mature, they become shallower. Shallow technologies in CRM projects enable administrators and developers to focus more on what the users want rather than on how the software works. In contrast, classic government and commercial projects often do deeper and trickier things with technologies. Some existing programs become easier. As the basic level rises, some programs that solve older known problems should get simpler and easier. New algorithms and commonly used components slowly migrate into standard libraries. As these libraries improve, developers can rely on them rather than rolling their own. Programs should slowly evolve to contain less algorithm and more glue. As databases improve, programs should slowly evolve to rely more on dynamic query optimizers. Suzanne Sluzer noted that contemporary programmers do more integration than innovation. Denning and Martel wrote, quote, "The best methods of design have been encoded into the structures of languages and operating systems." We would add that the best methods are also encoded into practices like processes and scripts. Some existing programs become more complete. As the basic level rises, many improvements in technology enable developers to change from doing things inconsistently in emergent ways to doing them consistently in deterministic ways, even when the total work increases. GUI programs tend to be much larger than command line programs because they enable flexible interactions and meaningful visual expressions. Quality improves as these programs become more useful and complete and handle more errors more effectively. As the basic level rises, user-oriented programs tend to get larger. More emergence becomes possible. However, improving tools and practices, i.e., making existing programs easier and more complete, differs from getting closer to knowing everything. As the basic level rises, the emergent possibilities of software engineering also continue to increase, and the power and scope of programs continue to rise. More improvements to programs are possible today than ever before. For example, sponsoring organizations have always found new opportunities to write bigger, more powerful programs that integrate on larger and larger scales. We expect that bigger and bigger programs will always get written. We believe that current CRM systems could not even be envisioned if programmers were still struggling to write machine code. The improving tools and practices fallacy occurs whenever someone thinks that solving an outstanding problem, such as improving tools or standards, will reduce the problems that remain. As the basic level rises, our concepts of reality and of software engineering rise. As expectations of science and society change, expectations of programs also rise. Odds and ends. Inspiration. The panel, The Algorithmic View of the Universe, in the Alan Turing Centennial Conference inspired our epiphany that deterministic concepts from computation had already strongly influenced society with processes and metrics. Eurocentric. The history of this chapter is mainly Eurocentric. Alas, we don't know enough about the history and philosophy and technology in the Middle East, India, and China to broaden the references. We hope that software engineers from those regions will do so. Irony. Using a reductionistic facet-by-facet analysis to describe emergence is ironic and wrong. This chapter merely contains a list of observations about emergence. Boehm. Working with this chapter has increased our respect for Barry Boehm's work. Barry Boehm and Richard Turner wrote the first book about combining agility and discipline. Barry Boehm also presaged aspects of Agile with the spiral model. Dialectical. Each section resembles George Hegel's dialectical method of thesis, antithesis, and synthesis, except that we don't actually synthesize anything into unified wholes. Vocabulary. 3 words used in this chapter have multiple meanings, which may confuse some readers. The word script means both code that glues algorithms together and article about knowledge. The word complexity means both fractals and chaos and the computer science concept of inherent difficulty. The word induction means both generalizing from examples, or more specifically, generalizing from statistical truth, and a proof technique used in mathematics.